To understand the various things, we'll first of all see the various atmospheric layers. The first layer, in which we are all there, ground level to approximately 10 kilometers above mean sea level, is known as the troposphere. 99% of the water vapor of the entire atmosphere is present in this region. 99%, that means almost the whole lot is present in this region. The air pressure and temperature in this region drops with increasing height. Ground level can vary from 0 degrees in the Arctic, for example, sub-zero. In the tropics, it can go up 30, 40 degrees centigrade. But as we go up in the atmosphere, the temperature goes down typically to 0 degrees Kelvin, 0 degrees centigrade, 0 degrees centigrade, around 3 to 4 kilometers above Earth's height, above the mean sea level. And then above 10 kilometers is called the stratosphere, approximately from top of the troposphere to 50 kilometers above mean sea level. This is mainly containing ozone in a large portion. The high energy UV light from sun produces considerable ionization in this region. This is a very important phenomena as far as lighting is concerned. It produces a lot of what we call ionization. That means dissociation of the neutral molecules of air, nitrogen, oxygen, etc., into ions in a substantial proportion. The temperature in stratosphere goes on becoming warmer with height. It lacks turbulence and updrafts. Because of the lack of turbulence and updraft, it's a very attractive zone for commercial aircraft to fly. There will be no turbulence. The flight will be quite comfortable comparatively. In the troposphere, there can be a lot of turbulence which can be felt by the aircrafts, and therefore it can be very risky also. That's why most of the commercial aircrafts take to the stratosphere region for flight, for the major port of the flight. Then we come to the mesosphere. It's above the atmosphere, above the stratosphere, up to about 85 kilometers above mean sea level. The temperature gets to minus 90 degrees centigrade at around 85 kilometers. The pressure is very, very low, approximately 1% of the atmospheric pressure. The standard atmospheric pressure is 760 millimeters of mercury at the mean sea level. That means the pressure is around 7.6 millimeters. 760 millimeters, 1% of that is about 7.6 millimeters. Is what we call in vacuum terminology as a soft vacuum. In this region of pressures, electrical discharge will be what we call glow discharges. What happens in tube lights, typically. Tube lights, there's a low pressure discharge or a glow discharge. Above the mesosphere, we have got the thermosphere, above 85 kilometers, and then the temperature here goes up to 2000 degrees centigrade. But in contrast, that what we can also say is air is very, very thin. It feels extremely cold. Now, why is this contradiction? We say very high temperature up to 2000 degrees centigrade on the one hand, and we say it feels very cold. Remember, temperature is a direct measure of the energy of the molecules in the air. Therefore, whatever molecules are there in the thermosphere, they are very, very energetic. But the so-called mean free path of this will be in hundreds of meters. That means if a person stands there, the air molecules will not collide with him frequently at all. So he's not able to feel the energy of these molecules. He feels only the coldness of the atmosphere at that temperature, in that region. Therefore, because of this, we say it feels very cold. On the other hand, the energy is very high, 400 degrees centigrade to 2000 degrees centigrade. The contrasting statements, this is the explanation for that. Then we have got the highest layer of the atmosphere, exosphere, is probably the final frontier of the Earth's surface, Earth's gaseous envelope. It's extremely thin. The so-called mean free path, or the distance between successive collisions of the air molecules, can be in kilometers, not meters, not centimeters, not even kilometers. It can be many, many kilometers. It is extremely thin. It leaks into outer space. The top of the exosphere is variously estimated to be 100,000 kilometers to maybe 190,000 kilometers. So this is exosphere. These are the overall thing. But for interest to us, from the lightning point of view, is what we call the ionosphere. This ionosphere is a very important parameter in the phenomena of lightning, particularly the lower ionosphere, about which I will be mentioning just a little later. Ionosphere happens to be what we call the positive electrode of the global capacitor. We will be talking about the global capacitor in some more details a little later. Ionosphere is not a distinct layer by itself. It's a mixture of a few other layers. It extends from approximately 85 kilometers above Earth to approximately 500 kilometers above Earth. The estimated electrical potential or the voltage with respect to Earth, it's not a small number, is 250,000 volts, 250 kilovolts to approximately 300,000 volts. That means 300 kilovolts. Remember, it's a huge voltage, and the lower atmosphere in particular has got this potential nearly constant with respect to Earth. That means Earth is an electric electrode with respect to Earth. This lower ionosphere is at a high potential, positive potential of 250 kilovolts to 300 kilovolts, which is nearly constant. Now, this high voltage here induces negative charges on the Earth's surface. It induces negative charges on the Earth's surface. The lower ionosphere, about which I mentioned as an important part of the lightning activity, extends from approximately 50 kilometers above Earth to 75 kilometers above Earth's surface. We call this the global capacitor, about which we'll see a little later. The lower ionosphere is also known as the electrosphere because of the electrical charge and the charge domain. Now, this is the picture of the so-called global capacitor. It is not really to scale. I have shown Earth and then the lower ionosphere. This is the Earth, of course, with negative charges on the surface all around, everywhere, induced by the positive charge in the lower ionosphere. This is the lower ionosphere, which is positively charged because of solar radiations, ultraviolet radiations, cosmic radiations, etc. It's ionized, and then it has got large amount of positive charges, and therefore it is the positive electrode of the so-called global capacitor. So you'll see that Earth is the negative electrode, and the lower ionosphere is the positive electrode of this capacitor, which we call as the global capacitor. Now, not to scale again, the cloud is shown here, typically around 2 to 3 kilometers above Earth's surface, up to about 10 to 13 kilometers above Earth's surface. Obviously, not to scale. Don't get worried about this dimensions. I have to make it clear to be seen by the audience. Therefore, I have shown it a little big. It will be just a line, nothing more than that. Above the Earth's surface, above the cloud, we have got a region where we have got the so-called transient luminous events, which were shown a little earlier. The sprites, the blue jets, tendrils, and the elves, they occur in this region. In fact, together, these cloud charges and the elves together take positive charges to the lower ionosphere. We'll be discussing about that much later, but we'll see this positive voltage of 300 kilovolts above Earth's surface is nearly constant. It varies between 250 kV to 300 kV. Sometimes there can be more fluctuations. Area-wise, there can be fluctuations. It may be more here, it may be less here. All these are statistical. Similarly, Earth will have negative charge. The charge density may be varying from point to point. We have got soil, we have got mountains with ice, we have got seas. So everywhere there can be variations. We can give the typical characteristics of these global capacitors a little later. Now, this global capacitor plays an extremely significant role in lightning and the transient luminous events. The characteristics of the global capacitor are now mentioned in this table. Now, to summarize the whole lot, the lower ionosphere, which we saw just a little while ago, is nearly 250 to 300 kV, nearly constant voltage with respect to Earth. Earth is the negative electrode. So this is the global capacitor. Now, the average leakage current now is about 3 into 10 to the power minus 12 amperes per square kilometer. The usual terminology in electroniering is that it's 3 picoamperes per square meter. Now, if you take a metal sheet of, let me say, 4 meters by 4 meters, mount it behind our backyard, and ground it through a picoammeter, we can measure some 50 picoamperes. Anywhere approximately maybe 30 to 50 microamperes, 60 picoamperes, you can measure it. So that shows you, yes, this is true. There's an average leakage current right from the ionosphere to the ground, and leakage of current from the lower atmosphere to ground. Now, the average charge density on the Earth's surface is approximately about 1.1 to 10 to the minus 9 coulombs per meter squared. Now, if you take the ratio of the voltage, 300 kilovolts, okay, I will come back to that again. The average current density I have shown you is 3 picoamperes per square meter. If you consider the whole Earth's surface, multiply the current density by the total surface area, the total leakage current will be approximately 2,000 to 3,000 amperes. This current leaks from the lower ionosphere to Earth. Why does it leak? It's a very interesting question. If air is a very good dielectric, ideal dielectric, this current will not come into picture at all. But the atmospheric air is getting ionized by the cosmic radiation, solar radiation, ultraviolet rays from various sources. It gets ionized. Every second, approximately 6 to 12 electron-ion pairs are created because the interaction of this cosmic energy with these neutral molecules of the air, that means nitrogen, oxygen, etc. All the gases, they get ionized. 6 to 12 electron-ion pairs are created. So this forms this helps to form the current. The positive charges come down to Earth. The negative charges go to the atmosphere, the lower ionosphere. So that forms the leakage current. So if you measure the total leakage current, that's the ratio of the voltage to the current, rather the ratio of the current voltage to current, use the effective resistance of the global capacitor insulation, so-called insulation, Earth to lower atmosphere, lower ionosphere. The resistance is approximately 100 to 150 ohms, which is here. Now, next thing is, what's the electric field at their surface? Remember, the potential of the ionosphere, lower ionosphere, is around 300 kV. Earth is a negative electrode. So what's the electric field at the Earth's surface? Typically about 3 volts per centimeter. So if you think of a man, approximately 1.5 meters tall, from head to foot, there will be approximately 4.5 volts. It's a very small voltage. It will not be sensed much because the current is too low, and the human body also acts as a near short circuit for these currents. The impedance of the Earth instead of the air around the person is much higher than the impedance of the body. Therefore, it nearly acts as a short circuit. The voltage is not felt really. Sorry, I made a small mistake. 3 volts per centimeter, that means 300 volts per meter. If you think of a 1.5 meters tall person, it will be 450 volts, which is a substantial voltage, but still the person does not sense any electrical shock because the current is very, very small. That is 3 picoamperes per square meter. A human person may be equivalent to approximately only 0.1 square meter. That means the current is extremely small. I must mention here that the electric shock is mainly due to the current, not the voltage. The voltage drives the current. It's the current which creates all the sensations, as we'll see a little later. It's always the current in the lightning which is a damaging feature. Current is the damaging feature. Current is a damaging feature. You can emphasize it many times. The voltage is the one which drives the current, but it's the current which causes the damages. So now, if you think of the lightning developing the ground from the cloud to ground, which we will see a little later, typical field on the Earth's surface goes up to about 400 volts per centimeter to approximately 600 volts per centimeter, just before the lightning reaches the ground. Now, the average equivalent current per lightning stroke is 2 amperes. Now, supposing this leakage current flows continuously, the capacitor must get discharged. If you take any capacitor or even a battery and short it, the voltage gets completely driven down to zero in a very short time. So why does this lower atmosphere remain at 300 kilovolts in spite of this huge leakage current of the order of 1000 to 1500, sorry, 2000 to 3000 amperes. It's continuously flowing. Why does not this global capacitor discharge and the voltage goes to zero in a very short time, maybe a few seconds? The phenomena which recharges this global capacitor, one of the major phenomena is lightning. So lightning is nature's phenomena of recharging the global capacitor and retains the potential of the lower ionosphere approximately between 250 kilovolts to 300 kilovolts. I hope this point is very clear. There's a very important thing because lightning is now nature's phenomena, one of the major phenomena of nature, which recharges the global capacitor so that it remains at a near constant potential of 250 kilovolts to 300 kilovolts. Now, estimate total number of lightning that takes place in the world per second is 3000 to 5000 strokes per second. The average equivalent current of lightning stroke is only 2 amperes. 2 amperes. So these are the major characteristics, electrical characteristics of the global capacitor. So now we will see what's the importance of lightning. Of course, now we'll go into the other aspects, the lightning, how it develops and things like that. But these are the basic features of the electrical phenomena of the global, I should say, global electrical phenomena, atmospheric phenomena, of which lightning is only one part. But it plays a very important role of maintaining the potential of the global capacitor nearly constant at 250 to 300 kilovolts. I think this summarizes this basic feature of the global electrical system.